Good evening, everybody. Let's just get right into it. Part 2, day 15. Get the background music going. All the good stuff. I want to make this just about an hour, if that. If I finish part 2, great. If I don't, great. Would help actually put that on. Okay. So, in any event, we're good. Okay. So part 2, I think, and I did look over this a little bit more. When you are pushing items to the right or left, I had to make sure that if the current item is a box, that you're getting the right position as our current position. And then what the item 2 would be is either a box with its left position just to your right. Go challenge playthrough. Yeah. Or I think this is one I had to fix. I think this is also right, and that was incorrect. Because if you're going to the left, you have to pick the left position and then find a box where its right position is just to the left of you. Okay, so those two, I think, excuse me, work. The fun one is going to be the up and down. And I believe what I need to do is put an entities to move as saying it's a new list of a hash set of entities. I could make it a list. I was thinking about this. I think if you're looking above or below you, you want to make sure that whatever you're doing to find what's above you, that you do it the same way. Okay. So our current item is what we always do before. We put a while true in here. Okay. And we say, now, yeah, this is going to be a little different. So when we say entities a move, add, it's got to be current items, a new hash set of entity. Can you do that with a hash set? Yeah, you can. So your entities to move are going to be current items. Okay. And then you have to say for each var current item in current items. Now you need to do this current position. Where is the current position of the item? Okay. And we're just going to arbitrarily pick, because you're either going to have a actually, you're only going to have, I just realized this, sorry. You are not going to have walls as current positions. So I don't know why I'm including that here, but that will not happen. So you would either say current item, otherwise current item is box dot right position. And you don't like that. Why don't you like that? Trust me. Trust me. So then you'd say current item as a box. Trust me. It's left position and you would never have a wall. Okay. All right. So we're back here. So we're going to do that here too as well. Current item as a box. And we're just going to arbitrarily pick the left position. It doesn't really matter because you're going to have to check both sides of it, but we'll know if whatever our current item is. We want to look at the whole row. Okay. So, yeah. All right. Now, what we need to do is say if it's a robot, And the next item is, so we have to say if current item, which this should be only like the first time, is robot R. And you're complaining about this. Yeah, because it's already, God, that sucks. Why does it do that? Why does it put it in scope like that? Whatever. Current robot. There. Naming naming is hard. So if the current item is the robot, then it's kind of like what we were doing before, which is we just literally, well, yeah, we just look above us. Though we have to be a little bit careful. So if it's a current, if the current item is a robot, then the next item is going to be a box where its left position is the same as our X, and its Y position is one above us. If it's a wall, then it's got to have its position as X, not X1, and its Y position is Y minus 1. If the next item is a null, then we break. If the next item is a box, then we say current item, is equal to a new hash set of entity with just that one item. Otherwise, we've already seen that there's nothing after it, either a wall or a box above it, and so we break out. Okay. And then what we have to do is kind of like what we're doing here. Sort of. So we get this. Yeah, the else condition here, if it's a box, that's where it gets a little tougher. And I realize this code is getting quite long, but I'm just trying to make sure it just works. So we would say if entities to move has a count, we say for entity no, I changed my keyboard. Entity items to move. The reason we want to change is we want to say for well, that's a bad name. And the T's to move. And then we say for each var entity to move and entities to move. Because that's the hash set. And so then we go through our entities, we remove them. If that was a robot, then our position stays here, but it goes up. If it was a box, same thing. We stay here, except we go up. Okay. Cute. Okay. So it's now the tricky condition of if our current item, because we're going through each item and that can end up being a row of boxes. And arguably, you can get it so you have a tree and you have spaces. That's why you want to look at each one individually. And if you add something above it, you've already added into the hash set, no big deal, because it will only allow uniqueness. So that's fine. So if it's this, fine. Else, we know it's got to be a box of our current box is equal to current item as a box. And in fact, we can just hard cast it because we know it's going to be that. Okay. So now we need to look at our left position. Do we even need this? I'm thinking we don't. Because we can just say the current robot's position. We don't need to do this here. So we get the box, and now we're going to say, okay, we need to if we find a box, or if we find the next item where the left position is the same as our left position, we just add that. We could say if its left position is equal to us or its right position. And then when we find the box, we say, well, if it's the left position that are equal, we're done, because then it's literally they're on the same thing. If it's right position equals our left, well, now we have to look at the right position and see if that could be a wall, that could be a space, you know, so we got to do that twice. That's where this starts getting to be quite messy. I know I'm really not being a very good coder here by going as far in as I am with something, but I'm just trying to see if it works. So, how do I want to do this? It's also if a wall, it matters. And if we don't find anything in either case, that still doesn't matter, right? This is wrong too. If the current item is a robot, it can be a box's left position or it can be a box's right position. It doesn't matter. Or we're going to do something or. Right. Or the box's right position. And the robot's just a 1. Just with the robot, we got to see, is the box either aligned above it with a left or a right position above it. And that's true. You'll only find one. So in this case, it's one. This one's a little trickier. We could find, because we are a box, we could find one or two things above us, right? We could find one and then that's it. It's just a box. It's over, but that just means that there was nothing else like a space. We could find nothing, which means it's just a space. We could find one box. So I think what we can say here is we can say entity select to list. That's what we're eventually going to do. So we want to find a box where either the left position equals the left position, that means it's right up above it. A left position equals a right position above it, that means it's over one. Or the right position equals the left. So it's either left, left, which would mean right, right equals, or it's left, right, or it's right, left. I know that, like, you're looking at me moving my hands and you're like, what the hell is he doing? But it makes sense to me. So I think what we want to say here, if it's a box and its left position equals our current box's left position X, and it's, wait a minute. Yes. And its left position Y is our current position box's left position Y. Okay. Or we could do this. If we have a box, we can do a search and say any, which means if you find any that are a wall above you, then you're going to hit this case, which means you can't move. So let's do that. If entities any, say E, where E is a wall, W, and the W's position X is equal to the current box's left position X, and so we're going to have the same thing here. Its position X is that. The wall's position Y is equal to the current box's left position Y minus 1, or it's equal to its right position. And so that means a box is above one or the other. Why are you complaining here? E is wall W and equal to that, and it's equal to that. I don't understand why it thinks it's not assigned here. It knows it's a W. We're saying it is a wall W, and then we do this. So I don't understand why it's complaining there. We break out. Okay, it's the same thing as if we hit the wall above. We could do the same thing here and make it a little bit cleaner, but at this point, sunk cost or something, I don't know. So now we could say else. We want to find where it's a box. We still need to do the list. Why do you not know? There. Okay. Whatever. So basically you want to put these in here, sort of. Except we're going to find next items. And if that is, it's not going to count as equal to 0. That means we didn't find anything, and that's basically space. Else, we know we've got a box. Okay. And we could potentially have just one, or we could have one that's right above us, one over, or we could have two. So there's 3 cases to keep in mind. Do we even care though? Right now, I don't see the difference between those two. So we're saying if there's a box, same X, but that box's Y is right above our left. That's what we do here. Or we're saying the box's right position is the same as our current box's, and its right position, so that's where you get that skew. Or you have one more case. The box's left position is same as our right, and its left position is the same as our right, but above. So that's where you have the skew over on the other way. Okay, so you're going to find at most 2. And this check should have already made sure that we didn't have walls above any of the boxes that we have above us. Right? The robot is a special case. We just have to look for the robot that way. Or a wall. If we don't have anything above us, then we just pretty much stop. What does this break out of, though? That breaks out of the for each. That doesn't break us out of the while. Which I guess this is turning into all sorts of fun. If we have the robot and we don't find anything, then the robot can move. Yes, so we would keep the current items we just break out because it's saying, yes, you can move. Otherwise, if we find a box, it's just a box that's above us. Doesn't matter which side it's on, it's just above us. Otherwise, we found a wall. And we clear the any items move because we're not going to do any processing with that. Okay. But this break simply breaks us out of the 4 each. And that's not good enough. We don't want to do this until we're done. Right? Yeah, we don't do this until we're done with the while. I think we need to do something to say like, potentially something where we keep a flag to basically say we need to like if we're told to break out of these two, we need to say something var is processing complete. It's false. We don't know yet, but if we hit this, we know we will. Here we will as well. Here we will as well. And we'll eventually know that down here too. And then this. What? Thank you. We do that here. Actually, yes, we'll do it here if is processing complete. Break. So that break goes with the while there. This is just saying you've hit a condition. No. Yes, if it's a null for the robot, then yes, we're done. If we hit a wall, we're done. We're just looking for boxes. If we didn't find any boxes. God. Somebody said yesterday it's all the corner cases you got to think about with this. We're looking at a box and we didn't find any above it, but that doesn't mean that the next box may find a wall. The next box may find another box, and we'd have to keep processing or boxes. So we can't just say, in this case, with the current box that we're looking at, just because we didn't find any items just means we got to continue. So we don't want to break out of the for loop. We just want to say continue. And that continues to the for. Okay. we've looked at our box and we've seen that there aren't any walls. So the only thing we can do now is look at the items and say current items is equal to a new, well, is equal to next items to hash set, right? Except it's not gonna like this because wait, why is it a he is a box in its left position. Still a bool. Why? Why is it doing this? I don't understand that. Now, else if the current item are robots, that's a special case. That's just the first one. I believe parentheses are needed after E as well. I'll come back to that. I gotta just figure something out here. If we have a robot, the most we're gonna find is either a wall above us or a box above us. If it's a box, we say current items is equal to, and this would be a new hash set, with this being the item in it. Fair. Except this one, we can't say is it just one, because you could have a list of robots above or boxes above you. And so we need to make that I never said I was a good coder. So these are going to be our new current items. Those are our current items. Once we get out of the current items for loop here, we could say current items is equal to new current items. Why are we doing this? Oh, that's all of them. Right. Okay. And if the processing is complete, we'd break up because we're saying we either found all spaces or we found at least one wall to stop us. Okay. So once we get out of the for each, yeah, we want to say current items is equal to all the ones that we found here. And then if we don't, if the processing isn't complete, we just go back up here to the while loop. We say any of the items moved are the current items. And now we're going to grab the new current items here. Okay. Sorry, this is getting messy. I am not going to deny up and down that this is bad code, because it is. I will come back here, Stefan, in just a second. So if we found any walls, we stop. We don't process any items. Here we're looking for a box. It can be directly above us. It could be where its right is over our left, or it could be where its left is over our right. So we could find two. If we didn't find any, we just continue. Okay. But there's a catch here. If we don't have any new current items, because that just meant we found spaces, right? We never added anything above us. Then we do this, which when we come back through, we'll add that next row of items above us. God, this is a mess. But in this else condition, again, we're not going to find this. The new current items I wish a hash set would have a add range. I really wish it did. I don't understand why it doesn't. And I get kind of why, because I believe an add does return a bool. It's kind of curious here that it's not flagging this to say, hey, you're not looking at the return value. You don't seem to care about it. Okay. So we could have 0, 1, or 2 for each box that we find. If our current item is a box, we're going to look for things above it. We don't find a wall. We don't find any boxes above it. That means it's space. Fine, we just continue. We don't add to new current items. We come through here again. We look for the next one. So if we have 3, and all 3 of them have spaces above both positions, then new current items will be empty, and we can say, well, guess what? We got to break out because we didn't find anything above us. Or we hit a case that tells us, yes, you need to break out because you either found a robot that has a wall above it, it doesn't have anything above it. Yeah, and that's just the case of the robot. Or it's a robot that has a wall above it, which means you don't have anything to process, you got to break out. Or we found a box that has a wall above it, either spot. Okay. And those are the cases. Now getting back to what you said, Stefan. I believe parentheses are needed after E is wall W, as the AND has higher precedence than the OR. But then why would this one work? Okay. I remember the teacher that taught me or tried to teach us C in college. He said, if you can't get something to compile, just add more parentheses. There you go. I need to add parentheses around both or combine position checks. That's what I did. That's what I did here. This parenthesis goes around both of them. So it's saying that entity above me, I need to find an entity that is a wall, and then it's either going to be this condition or it's going to be this condition. So that seems to work. Okay, I get it. There's a delay. And there's a delay in what you're... When I say something, I think it's like 20 seconds, 20 or 30 seconds, so no worries. And the same thing down here then, too. Okay, this is god-awful code. Let's look through it again. And I still have to do the down, which hopefully should just be kind of like reversed everything I just did for the up, but who knows. So let's go through the up again. So if we find an up, what we're going to do is we're going to find entities to move. And that's going to be a list of hash set, because each thing above me is going to be a row or a list of items. And a hash set just makes it so that I can only add a unique item once, because you could have a box where its right is, its left is above a right and its right is above a left. So it's actually over, one box is actually over two boxes. But we don't need to process that twice, so that's why I'm making it a hash set. Then we say our current items right now would be the robot. Okay. And then we go through our while loop, except it's a little bit more complicated than this. We add two items that we're going to move, which first case will be a robot. And we say, what are our new current items? Okay, well, let's go through each current item and current item. If it's a robot, well, we know that we'd actually only do this once. So what we're going to do is say, well, the only thing it could be is if there's a box above us where its left position is these coordinates, or its right position is these coordinates. Or we have a wall that's directly above us as a robot. If we don't find anything, we're done. That means the robot can just move up one. And so that's what we're going to break out eventually. Because if we go outside the for loop here, that's one of the conditions. Okay. If the next item is a box, fine. We add it to our new current items. And technically, we could just break here. We're going to fall out anyway, because we know if we have a robot, that's the one case right at the beginning. Okay. No big deal. So we would fall out of the for loop. We would see that we have one item, so we won't break. We'll set that up. And then we would, as we go through it, we're now going to add those current items, which is the box we just found. Okay. Otherwise, we found a wall. That's this case, right? We found a wall. And that means we can't move at all. And so we're going to clear everything out. We're going to set processing complete to true. We're going to break. That's going to break out of the for loop. And we're going to see that we're going to see its processing is complete. And so we break out. Now break out of the while loop. We'll see that we have no items to process. We don't move anything. Okay. So that's if it's a robot. Else, we know it's got to be a box. That's the only other thing we would keep track of in our hash sets. So we automatically cast it to a box. And now we're going to say, is there a wall above this box? And to have a wall above us means it's the same X left position, but that wall's Y is equal to, oh, that's crap. No, that's right, because we're at the current box, and we'd be at 3, and so we're looking at 2. Yeah, okay. I'm just trying to not assume I wrote it right the first time, or the 5th time, or whatever iteration we're on right now. Or the wall's right position is the same X, and its Y is 1 above us. If that's true, we've hit a wall, nothing can move at all, and so we clear out, say we're complete, and we break. Else, the only other thing we are interested in are boxes above us. So we look for a box that's directly, it's basically the box 2 positions are basically covering our box. Or that box's right position is over our left. Okay. Or that box's left position is over our right. These Y coordinates don't really matter because they're going to be the same for the left and the right. It's the X's that matter. Okay. So we're either going to find 0, 1, or 2. If we don't find any, that means we're not done. It just means there was nothing above us, so we don't add anything to new current items. Otherwise, we're going to add the 1 or 2 we find, and because it's a hash set, if we ran into that case where we're like doing 1 and then 2 and then 3, where that middle one would have shown up in both queries for those 2 underneath it, it would only be added 3, and so we're only going to process 3 now. Okay, so we go through this, we come back up here. If there was a second box, we're going to process that. And eventually we come out with a processing where maybe we find that we have 1 box, or 2 boxes or whatever above us. Doesn't matter. If we don't find anything, we break out. Okay. For the case of new current items, it just meant that we may have had 4 boxes where there's literally nothing above us. That means all of this is going to move now. Okay. So whenever we said is processing complete, we're really just saying, oh, not here though. This we do want to process because that means it's just a robot that had nothing above it and it can move. Okay. This is a wall. Yeah, these are always different. I always got to look at these a little differently. Okay. If we get to the point where we actually have items to move, then all we're going to do is take each entity in these and say if it's a robot, we make a new robot by taking its original position and moving it up y-1. Otherwise, it's a box. It has to be a box. Whatever. And we add to our entities. Well, we've removed it. Now we're going to add a new box where both of the left and right positions move up by 1. Okay. So now we want to do the thing for the down. Okay. So now what we want to do is find it where it's +1. +1. +1. Because we're looking that way. That way. We're going to look down. That logic is still the same. This one is also, though, +1. +1. And these would also be +1. And these would also be +1, +1, +1. Who wants to bet if this is going to, at least for the test, there's a part 2 test here. And I'm going to bet against myself. I know myself better than this. It passed. That's why I don't bet. Because I suck at betting. Okay. Well, what's part 2's answer? Yes! Woot. Woot. Yay! I'm happy. If that wasn't going to work, you know, I've done Random.Code now for 2022 and 2024. It's okay if something doesn't work when I'm using against the test data solutions. It kind of sucks when it doesn't work with the actual run of the big data set. Because then you're like, oh man, did I really screw something up or not? And this one felt a little squirrely, but I'm glad I listened to, I think his name's Daniel. I think it's Daniel. Where he said he was debugging day 15 a lot because of all the corner cases. And I get it. You know, you really have to be careful with this one, at least in my opinion. And I could clean some of this up. You know, this is definitely not the most wonderful code I've ever written in my life. That's for damn sure. But it works. Yeah, impressive right on the first run. I am old enough, I keep saying this, I'm old enough to know that it never works the first time. 50% of the time it works all the time. What's that phrase? I forget. That's from Anchorman, isn't it? I don't remember. But you noticed how I had to sit there for pretty much this whole stream, which is like, I'd say at least, you know, how much time was I going through it and just making sure, was this right? Was this right? And yeah, it was not easy. All right. I'll at least look at 16. Let's see if we can get something out of 16. Yeah, look at the calendar. 30 out of 50. That's 60% done. That's a D- in America, or at least where my kids go to school. All right, reindeer maze. Reindeer maze. It's time again for the Reindeer Olympics. This year, the big event is the Reindeer Maze, where the reindeer compete for the lowest score. You and the historians arrive to search for the chief right as the event is, about to start. It wouldn't hurt to watch a little, right? The reindeers start on the start tile marked S, facing east, and need to reach the end tile marked E. They can move forward one tile at a time, increasing their score by 1 point, but never into a wall. They can also rotate clockwise or counterclockwise 90 degrees at a time, increasing their score by 1,000 points. I can already see where this is going to go, sort of. To figure out the best place to sit, you start by grabbing a map, your puzzle input from a nearby kiosk, for example. Zoom in here for people to see. So that's an example here. So look, it's a maze. Ooh, you can go up here and then over here and then down here and then up. There. Boom. There are many paths through this maze, but taking any of the... What's that called? A star or A path? That finds you the shortest path or something like that. But taking any of the best paths would incur a score of only 36. This can be achieved by taking the total of 36 steps forward and turning 90 degrees a total of 7 times. Ugh. Because I'm looking at this and I'm saying, well, if you don't know right away, and you are facing east, right? So like you're facing east, you would go this way, and now you're here. Then you go here. And now you're like, well, no, I can't go east. So now I have two possibilities. I can either go up or I can go down. Well, if I go up, can't do that. I already know I can't go right or east. You can use direction like that way. Can I go west? Yes, I can go west. This one could also be west. So like each, okay. So we'd end up coming back this way. We'd end up coming back this way. Eventually you realize, this is a way I could go, or that's another wall. You know, if you hit a wall, you have to look, are you going to turn around, which would be 180 degrees, but have you already traveled over those, you know? And in that case, yes, you have. If you're going to go, you have to go backwards. But if you basically end up going over the same path, and you keep bouncing back and forth as you do, like if you do 180s, do you end up, like, eventually you're going to get out though, right? I mean, at some point, you have to get basically back out and backtrack and then keep going the way you're going. I don't know. That's just random discussions of ideas. Taking a total of 36 steps forward and turning 90 degrees. For a total of 7 times. I still don't quite, because you 1, 2, you have to turn, 3, 4, you have to turn 5, 6, 7, 8, you have to turn 9, 10, you have to turn 11, 12, you have to turn 13, 14, 15, 16, 17, 18, 19, 20, you have to turn 3, 4, 5, 6, you have to turn 7, 8, you have to turn 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 36 steps forward. Well, I guess maybe I'm reading this a little bit too literally, that you can only go that direction right away, right? If you ever end up with something that basically makes you turn around, then you need to basically cut off that branch, because that was a dead end. Like you look at this and you say, what are the two ways I could go? I could either go up or I could go this way. Okay. This is only one direction. This, other than what's behind me, I can't go anywhere else. That's dead end. This 1, 2, 3, 4. Turning it 90 degrees total 7 times. So 36 steps forward. Let's do the steps forward. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 2, 2, 3, 2, 4, 2, 5, 2, 6, 2, 7, 8, 30. 1, 2, 3, 4, 5. Boom. 30. That's the 36 steps. Okay, we go up. That's a turn. So that's 1, 2, 3, 4, 5, 6. Why does it say I have to turn total of 7 times? Oh, because I'm currently facing east. I would have had to turn that way to go up. So only on the first one, like if I have to change direction from the way I'm currently facing, that's a turn. Okay. I get that. So this has to be a turn and then go that way. So that's 1. This has to be a turn and go that way. That's 2, 3, 4, 5, 6, and that's where you get 7. Okay. So yeah, if you have to change direction from where you're currently facing, you just have to say that's a turn. So the number, okay, here's a second example. Great. In this maze, the best paths cost 1,048 points. Following one such path would look like this. Up, over, and I get it because a legal path is, if you're here, you go here this way. You go up, you go over, you come over in here, you go up, you go over here, or you could just, you could actually do it wrong and then come back over this way, make it really long, and then come down. But that cost is going to be more than the cost of this. This is the most optimal path. So at each point you have to say, and this is where the explosion of paths come into play, I bet, because at each point, if you can go a different direction, even if it, like here, I could say, well, I'm not going to turn, but this is a valid way to go, and this is a valid way to go. It's just, I got here, this doesn't cost me a turn. This does, right here. This costs me 1,000 points to turn here. And so I can see where it's possible that a longer path, like maybe you actually go up, over, down, over, up, and over. Whereas if you did something here, you go over, up, over, up, over, up, over, up, over, up, over, up. Like that might actually be less points, but a lot more turns. And so that ends up costing you more. Okay. Note that the path shown above includes one 90-degree turn as the very first move. Yes, rotating the reindeer from facing east to facing north. Analyze your map carefully. What is the lowest score a reindeer could possibly get? I have the gut feeling that the second map is going to be like, you need to go from the start to the end, but you need to do it like 1 billion times, and then the cost changes on each one, and it becomes an explosion of path finding. And it's not just this, like I said, it's not just the shortest path. You can't just do that. It's weighted. It's weighted by how many turns you're doing. And you can have a monster mess like this, which is usually what, as you do. Right? So again, it's the same case where we don't have to keep track of an X max or Y max, because the entire map is surrounded by walls. Okay. So this is day 16. Okay. Let's get stuff set up here. $16. We can count, right? Can we? I don't know. Can we count? I don't know if we can. We're on part 1. Yes, we want a... Wait. Haha. Boom. Get rid of all of them. God, who wrote this crappy code? Let me tell you. Now let's just get rid of all those. I always like having abstractions for a specific thing. That's why I always put them in their own namespace, because then I don't have to worry about, is this point here is the same point there, because it might not have the same meaning, you know. we'll just say var count is equal to the input length, or the cost. Return cost. We want to have an enum direction where we want to say west, north, come on, kick in, east. No, not northeast. How dare you? So we need to have some way to say, are we facing a current way? Okay. And what we could do now is say a reindeer has a direction of a current direction and a position, right? So we could also say public enum position int x int y. And so what we want to do again is we want to parse and say, basically, we want to find the start, we want to find the end, and we want to find all the, well, we want to find all the walls. And we want to find, yes. Oh, that's, I did that wrong. Okay. So we could also have the notion of an public sealed record, an item, a map item, where the char is its type and its position is where it is. Okay. And so the first thing we can do is basically parse the file. So we'll have a private static immutable array of map items. I do that all the time. Parse input. Thank you. So we're going to say here is var items is equal to a new list of map items, and we'll return items. Hey, I didn't need a stupid code fixer suggestion to tell me to do it right. So we're going to say is for var y is equal to 0, y less than input, y plus plus. Thank you. And then we're going to say var data is input y, doesn't matter, for var x. Thank you. We're going to get var map. We're going to get var, we'll call it map type, is equal to data's x. Okay. If so we don't care about those. We don't want to keep track of all those, because we're just going to link the hell out of this like we've been doing. If the map type is equal to an S, or the map type is equal to, why would you do that? An E as a character, or the map type is equal to a wall. Then we say items add a new map item with the map type, a new position, X and Y. There. We can still say var minimal cost is equal to nil. You know what I meant. Okay. And I don't think I'm going to get this done, but I'm going to keep going for a little bit longer. So let's get our test cases set up. They're not going to pass, obviously, but we want to at least get so we have a small and a large, right? So here's one example, and this is technically smaller. So we'll put that in there. We'll say 16. And this should be that, which of course we're not going to be, but that's okay. Let's take a larger example. Put that in there. 16. And what should this be? That. We don't have a part 2 yet, so we'll just cut that out for now. And again, what I want to do is make sure that I'm actually parsing what seems to be correct. So we have map items, 123. When we get into the ones, we should have found an E. And then way at the bottom here, we should have an S somewhere. Yes, we do. Okay, so that looks reasonable. Okay. Map parsing for part 1 of day 16 seems complete. Ah! Save and commit. Thank you. Okay. Ah, solution. Make sure to commit that. Oops. Okay. We want to find paths. And paths are a list of ordered coordinates. So like, what actually did you take as a path? But it also it's also like, how many turns did you do? What is the path you took? And of course, as you make a path, because you can bifurcate, like maybe you hit a case where you could turn, like if you can go more, the most you can do is 2 different directions from a current point, right? So you can keep going the way you're going, or you can take a left, or you can take a right, or if you're, go down, depending upon if you're coming right. Well, let's just take the case of we're going north. So either we could go up, or we could take a right. Both are valid, or left, or whatever. Or right. You could hit a plus sign. And so you have 3 different ways to go. You never check the 180 because that just takes you back the other way. Yeah. If you can't do any of those, that path is done. It's deleted because you can't go anywhere from there. If you're gonna move, then you have to say, okay, my current direction is this, but did I change direction? from where I was, the direction I was going. Because if it is, then that's a turn. So a path basically is a list of points and the number of turns you're doing. The number of turns you've done and what is your current point in your direction. That's your reindeer. So you start with the reindeer. You say, can I, if my direction is going up, I say, can I turn left? If I can turn left, well, then I move my reindeer to go left. I drop my previous point. I put my current position in as a part of the path. I change my reindeer's position. And I also notice that now I'm going a different direction, so I have to increment the number of turns I've done. If I don't have to change direction, I create a new reindeer poop point or position of where I was, but I don't change direction. If I can't go any direction other than turning around, that's a dead end, and that whole path gets removed because that path just doesn't go anywhere. Okay. I wanted to walk through that in my head going, I kind of think I know what we need as an abstraction. And I think we're going to need something that's mutable that we're going to add on to and just say, okay, I have a reindeer and I have maybe we say, like a path can produce 0 to 3 new paths, if you think about it that way. Where one of those 3 paths may just be one added on with no change, and the other ones are changes. So maybe we keep this immutable. And so you have a path which starts with no positions and a reindeer. Okay. And then you just keep going through your list until you hit the end, which then that's a completed list, and you remove it. You have to turn around, which then you remove it, or you go ahead. So eventually you're going to hit a position where you got to the end, or you have to turn around. And so eventually it's going to stop. What we could also do as an optimization is say, if I did a path A, and that gives us a cost of C, then maybe a path B is longer, and it's already going to cost more than A. Stop doing B. There's no way, I think, in that case, to make it any cheaper. You're just going to be adding on to it. So no matter what paths it could do, no matter what it can accomplish, you basically only keep the cheapest map around, the cheapest path around. Right? And other paths can be explored so long as their cost hasn't gone over what we know is the cheapest one. And of course, we can't start making that check until we've discovered at least one. So when we discover a completed path, that becomes the cheapest, and we evaluate any maps or any paths in progress to that value, and any that are at or above because if it's equal, it means it hasn't completed. And even if it just moved one and that's a point, that's still more. There's no reason to keep going. So you can just drop all those off. Any that are under, they keep going. And when another path comes in, or paths, because you could potentially have more than one path, stop. They took different directions, but they ended up with the same number of steps. Okay. So you take one and you evaluate all the other ones against it. Or you basically say, what you do is you take all the ones that have finished, you find the cheapest one of that, and then say, is that cheaper than one that you found before? And then you say, now let's evaluate all the ones in flight. I think that makes sense to me. So now we just have to code it, so, which is always fun to do. So let's do one quick thing before I stop. And then we'll say wall. And that's cool because, again, if we're like looking in directions and we say, hey, find me one that's above me, to the right, left, and whatever, and we don't find anything, that means that's a way to go. So that means that the query is a little bit harder because you can't just index into a specific spot, but that also means we don't have to keep all of the entirety of the maze around. We get rid of the empty space, the spots that we can move around. Okay, cool. One thing I want to do before I end, I just want to see where it's at right now. If I came in here and I said run all of them, and let's put us in the release mode, not that that's going to make a big deal. The only one we won't do is part 2 of 14. And the reason why is that's the one that draws out, if you remember, if you saw that stream, that's the one that we're actually drawing out to see where the Christmas tree was. And so that would skew it. I'm just curious to see how quick does this take to actually run. I just want a clock. Clock needs an update. Gee, thanks. I appreciate that, You're going to want to update, stay on timer. Not timer, stopwatch. We're going to do a quick and dirty stopwatch, okay? Nothing fancy here. And I'll move it down here so I can see when this actually starts running, and then I'll so right now it's taking, again, this is just ballpark, about 9 to 10 seconds to run for all 15 days. So on average, some of them took a little bit longer, as you saw, but on average, and I have not done really any optimization, any really hard optimization to look at what could I squeeze out of some of this stuff, if anything. And I just haven't done that yet. So it's possible I could get this to be even quicker. We'll see. I don't remember where I saw this. I think I saw somebody mention that they were doing like some kind of benchmarks on the performance of their code, which is great. I mean, I did that when I did 2022. I went back and said, maybe I can make this a little bit better. Maybe I can make this a little bit faster. And I might do that with this. But right now, it takes about 10 seconds for it to get through 15 days. Now I'll take that for what it's worth. Maybe that's good. Maybe that's bad. More work on part 1 of day 16. And actually, before we do that, let's just keep it like that, like what we're doing. Git commit. There. All right. I don't know when the next time is I'm going to be streaming for Random.Code. Like I said, I wanted to get past really 15. That was my goal. I'm going to be doing a Splinter Cell stream tomorrow night. Wednesday, I have self-defense. And I also have to start working on some presentation materials for a conference in March. So I got to get that squared away and put together. So yeah, there's going to be some time to not put to this in the next couple of months, which kind of sucks. I really have every intention of trying to get through all 25 days. But time is going to make that too. I don't know when I'm going to be able to get all 25 days done. I just don't know. I don't know. But I'll try to keep making progress as much as I can. So with that, I'm going to stop the stream. Thank you for watching. If you haven't subscribed to the channel yet, please do so. I would greatly appreciate it. And with that, I will be on tomorrow night doing some more Splinter Cell. Take care, and I hope to see you in the